The more I dig into the physics, the more I realize something else might be true. The universe might not be infinite at all. Now, before you dismiss me, before you think I'm just being controversial, let me explain what we actually know from modern cosmology and from some deep principles of physics that I've spent my life working on. Because the answer touches on something profound that will change how you think about reality itself. Let me start with what we observe. We have these amazing satellites now. We have the Planck satellite, we have WMAP, and they've mapped the cosmic microwave background radiation with extraordinary precision. This is the afterglow of the Big Bang, right? And what we find from these measurements is that the universe is flat. Flat. It's like, imagine a sheet of paper extending out in all directions. That's what the universe looks like on the largest scales. It's flat. Now, what does flat mean? In the context of general relativity, flatness means that the curvature of space is zero. Einstein's equations tell us that the curvature of space is related to the amount of matter and energy that's in it. So we measure this and we find the universe is remarkably flat. And most people hear this and they jump to the conclusion that therefore the universe is infinite, an infinite flat sheet, like graph paper that goes on forever. But here's where it gets interesting. Here's where most physicists, even cosmologists, don't really think carefully. Flat doesn't mean infinite. This is the key point. You can have a flat surface that's finite. Let me give you an example. Take a piece of paper, an ordinary piece of paper, and roll it into a cylinder. Now, the surface of that cylinder is locally flat. If you draw two parallel lines on it, they'll never intersect. But the cylinder isn't infinite. You can go around it and come back where you started. Now, imagine something even more interesting. Imagine rolling that cylinder one more time, connecting the two ends. You get what mathematicians call a torus. It's like a donut shape. The surface of that torus is completely flat. Locally, there's no curvature, but it's finite. You can traverse it completely. This is a deep geometric fact that most people don't know about. So here's the situation we're in. The universe is flat. We know that with high precision, but we cannot definitively tell from observations alone whether it's an infinite flat universe or a finite flat universe with a donut-like topology. We haven't detected any repeating patterns in our observations of distant galaxies. If the universe were like a small donut and we could see across its diameter, we'd see the same structures repeating. We don't see that, but that doesn't prove it's infinite. It just means if it's finite and toroidal, it's so large that we can't see all the way across it. And here's the fundamental issue. There's a limit to what we can observe. Light travels at a finite speed. The universe has only existed for 13.8 billion years, so we can only see out to about 46.6 billion light years away. That's our cosmic horizon, our light cone. Beyond that, we can't see. Anything beyond that is, by definition, unobservable to us. And here's the profound statement. We might never be able to determine definitively whether the universe beyond our horizon is infinite or finite. The problem might be unanswerable. But now let me tell you something even more radical, something that comes from the deepest principles of physics that I've worked on. And this is where it really gets strange. In the 1990s, I was working on black hole physics. Stephen Hawking had shown that black holes aren't truly black. They evaporate. They emit radiation. They have a temperature. This led to a profound puzzle. If a black hole radiates away and disappears, what happens to the information that fell into it? This is the black hole information paradox, and it was one of the most troubling problems in theoretical physics. Now, my colleague Juan Maldacena found something remarkable. He discovered a duality, a mathematical equivalence, between a gravitational theory in a space called anti-de Sitter space and a quantum field theory on its boundary. This correspondence showed that the three-dimensional world of particles and forces could be completely described by a two-dimensional theory on a surface. It's like saying all the information about a three-dimensional volume, everything that happens inside it, can be encoded on a lower dimensional surface at the edge. It's literally like a hologram. This is the holographic principle, and what it tells us is something absolutely shocking. The information capacity of the universe is not determined by its volume. It's not infinite. It's determined by its surface area. According to the holographic bound, the maximum entropy, the maximum amount of information that can exist in any region of space, is proportional to the area of the boundary, not the volume inside. This is completely different from what you might naively expect. Now think about what this means. If the information capacity of the universe is finite, bounded by surface area, not volume, then the universe itself must be finite in a deep thermodynamic sense. There's only so much information that can fit in the universe, only so many degrees of freedom, only so many distinguishable states. If the universe were truly infinite, you'd have infinite information, infinite degrees of freedom. But the holographic principle says no. The universe is fundamentally bounded. Now, I'm not saying that the boundary is at 46 billion light years. That's not what I'm saying. The actual size of the universe could be vastly larger than what we can observe, but there is a bound. There is a limit. The universe is not infinite in any reasonable thermodynamic sense. And here's something else that gets people thinking. In my work on holographic cosmology, connecting the holographic principle to cosmology itself, we've found that the structure of the universe at the largest scales is constrained by these information bounds. The number of different configurations the universe can be in is finite. The number of possible states is finite. In a truly infinite universe, every possible arrangement of atoms would occur infinitely many times over, but our universe isn't like that. Let me give you another way to think about this. There's an old paradox called Olber's paradox. If the universe is infinite and filled with stars, why is the night sky dark? If there were infinite stars extending to infinity, the entire night sky should be ablaze with light. The fact that it's dark tells us something. It tells us that either the universe is finite or the universe is young enough that light from distant stars hasn't reached us yet, or the universe is expanding, and those distant stars are moving away from us faster than light can travel to us. We know that last part is true. The universe is expanding due to dark energy. But here's the thing. Even with expansion, even with the finite age of the universe, we're looking out at scales of billions of light years. And you don't see repeating patterns. You don't see the kind of redundancy you'd expect if the universe cycled back on itself. But that doesn't mean it's infinite. It just means it's either infinite or it's so large that we can't see the boundaries. And then there's the question of dark energy, the cosmological constant. This is something we discovered in 1998. The universe is accelerating. It's expanding faster and faster. And we don't understand why. We call it dark energy. It makes up about 68% of the universe, and dark energy has some very strange properties. One of those properties is that it creates an event horizon. Even in an eternally expanding universe, there are regions from which signals can never reach you because they're beyond your horizon and moving away faster than light. This event horizon, the boundary beyond which you can't see, it has thermodynamic properties. It has a temperature. It has an entropy. And that entropy is proportional to the area of the horizon, just like with black holes, just like with the holographic principle. The universe you inhabit, the observable universe, the part of the universe that you can ever have any causal contact with, has a finite entropy, a finite amount of information. And here's the kicker. If your observable universe has finite entropy, finite information content, then from an information theoretic perspective, you're not in an infinite universe. You're in a finite universe. Even if the mathematical infinity extends beyond your horizon, the part of the universe that matters to you, the part that interacts with you, is finite. It's bounded. Now, I know what some of you are thinking. You're thinking, but wait, couldn't there be infinitely many separate universes? Couldn't there be a multiverse? And yes, that's possible. In fact, my colleague Andre Linde worked on eternal inflation, and he showed that inflation creates a kind of multiverse, different regions of space, where inflation ends at different times, creating separate bubble universes. Some of those regions might have different laws of physics, different constants of nature. It's a wild idea, and there's some evidence for it. But even in the inflationary multiverse scenario, individual universes, including ours, are generically finite in extent. The total volume produced by inflation is huge, but it's bounded by the physics of inflation itself, and the multiverse, if it exists, doesn't extend infinitely backward in time. Inflation can't have gone on forever. Something must have preceded it. So let me sum up what I'm telling you. The universe is probably not infinite. Here's what we know for certain. First, the observable universe is finite. We can only see out to our cosmic horizon. That's a fact. Second, the universe is flat, but flat doesn't mean infinite. You can have finite flat spaces. Third, our observations haven't shown repeating structures, so if the universe is finite, it's large, larger than the observable universe by a lot. Fourth, and this is from deep principles of quantum gravity, the information content of the universe appears to be finite. The holographic bound tells us that any region of space has a maximum entropy proportional to its surface area, not its volume. This fundamentally limits how much information can exist. Fifth, even accounting for dark energy and cosmic expansion, there are event horizons in our universe, and those horizons have thermodynamic properties that reflect finite information. Sixth, in reasonable inflationary models, which explain the large-scale structure and properties of the universe that we observe, the total volume is actually finite, not infinite. Now, does this mean we'll ever know for certain? Probably not. Our observational capabilities are fundamentally limited. We can never look beyond our cosmic horizon. We can never leave our universe and measure it from outside. There are limits to what questions are answerable in principle, but I'll tell you what bothers me about the infinite universe idea. It bothers me because it's too easy. It's too convenient. When you say the universe is infinite, you're kind of giving up on the problem. You're saying, well, anything that can happen will happen infinitely many times. But that's not how the universe actually works according to our best theories. The universe has constraints. It has a history. It evolves according to specific rules. The finite universe idea, or at least the idea that the universe is bounded in a deep thermodynamic sense, this is more interesting to me because it tells us something. It tells us the universe is a system with a finite information content, a finite number of degrees of freedom, like a giant computer, you might say, a finite discrete system underlying reality. And you know what? That actually solves some problems. The black hole information paradox becomes easier to understand when you accept that the universe has finite information. The question of why there's anything rather than nothing becomes easier to address when the universe isn't infinite and eternal. The deep questions about initial conditions become tractable when you're dealing with finite systems. So, my claim is this: when you really dig into the physics, when you look at the observations carefully, and you take the holographic principle seriously, the evidence points to a universe that is, in a very deep sense, not infinite. It's bounded, it's finite. Maybe we'll never see the boundary. It could be far, far beyond what we can observe. But it's there. The universe is not a truly infinite system. And that changes everything. Because if the universe is fundamentally finite, then the universe itself becomes something that can be understood in principle. It becomes a closed system. It has a finite history, a finite future, and a finite amount of information encoded in it. And that might just be the key to understanding what the universe really is. That's what I found. And I think it destroys the conventional assumption that most people make about the infinity of the universe. The universe is probably not infinite. It's probably bounded. And understanding that might be the next big step forward in theoretical physics.